This is actually chapter 20 of the conceptual physics book. From our general discussion on waves, you remember that there were two main types, electromagnetic and mechanical waves. Mechanical waves require something through which to travel, called a medium. Sound is a mechanical wave. It needs something to travel through. It can't travel through the emptiness of space. We also talked about two main ways in which waves are generated. Either transverse, where the medium vibrates perpendicularly to the direction of the wave. So if the wave is traveling this way, the medium vibrates up and down this way. And longitudinal, where you have alternating areas of more or less dense areas called compressions and rarefactions. So compressions would be these areas where the slinky that we use to demonstrate a wave would be tighter together, and rarefactions would be where it's less dense or farther apart. Our hearing in general ranges from 20 vibrations per second to 20,000. Remember that K means kilohertz, 20,000. As we age, we tend to lose this upper end here. For example, your teacher can only hear about 13,000 hertz because of damage that's been done particularly to the upper end of this hearing range. We use the word pitch and frequency interchangeably out there in the big world. Understand that frequency is a physics concept, it's a science concept, it's the actual number of times something goes back and forth, where pitch is our perception of a particular sound frequency. In air, the speed of sound is about 340 meters per second. So for problems, we're going to use that in this equation. If you remember, this is the wave equation that relates frequency and the wavelength of a wave to its speed. In any particular medium, the speed of a wave is going to be constant. And this makes sense from the point of view, for example, of going to see an orchestra performance. If the speed were different for different instruments, then all those instruments would have to play at different times so that the sound would get to the audience at the same time and create an enjoyable experience. A quick example here, it's not really applicable anymore. Back in the early days of cell phones, there was a secret ringtone that students could download called the mosquito ringtone. It was magic because teachers couldn't hear it, but students could. At least that's what the myth was. The reason some teachers couldn't hear it is, remember, we said that the top of human hearing is somewhere around 20,000 hertz, and as we age, we lose the ability to hear those higher frequencies. So for example, if you had a ringtone that rang at 18,000 hertz, I would not be able to hear it. So in solving a problem like this, remember, kind of label stuff that's in the problem. You've got the wavelength is what we're looking for. The frequency is what's given. Again, remember this is 18,000. That's why I put 18,000 inverse seconds. Remember, an inverse second is a unit of frequency called the hertz. And it didn't give me V here, but if we're assuming that a ringtone from a phone is traveling through something, it's probably going to be air. So that's where I got the speed from the previous information, previous slide, that the speed of sound through air is about 340 meters per second. Grind it out in your calculator and you get this answer, or it's about 1.9 centimeters. Here's just a general relationship. Sound travels fastest through solids. It travels the slowest through gases, and it kind of makes sense. In a solid, particles are usually very close to each other and they're attached to each other. The sound wave travels very quickly through those attachments. At the other extreme, because gas molecules are typically far apart from each other, it takes time for information to travel from one particle to the next, and therefore for sound to travel through that. Again, this is a general relationship. That's all you're responsible for. We had previously talked about the Doppler effect. Here's another example or a reminder of it in the case of sound. Do remember that the Doppler effect does apply to all waves, okay? And again, the effect is the result of the motion between the source of a wave, in this case a sound wave, and the receiver of a wave. If the two are getting closer together, a higher frequency is perceived. If the two are moving farther apart, a lower frequency is perceived. Now again, it doesn't matter which one's actually moving. If one is moving relative to the other, you will experience this thing called the Doppler effect. I'm not going to spend too much time on this slide because there are separate videos that we're going to watch dealing with this. But things that vibrate do so at natural frequencies. So if you drop a fork on the floor in the kitchen, the sound you hear is based on the natural frequency of vibration of that fork. Resonance is a phenomenon where we can cause something to start vibrating without actually touching it. So for example, you can get a bell to ring by hitting it, but you can also get a glass to vibrate by singing a particular note that matches the natural frequency of the glass. Maybe you've seen opera singers shattering glasses by doing that. That's called resonance. Resonance is also the phenomenon of pushing a kid on a swing. When you apply an external force, namely the push, to that kid at just the right time, the kid starts vibrating higher and higher, a bigger and bigger amplitude. The swing has a natural frequency, and you have to match that natural frequency with your pushes, and when you do that, something called resonance occurs. You remember in the chapter on waves, we talked about interference. Interference is when two waves are at the same place at the same time. Beats is a phenomenon that happens when you have two sound waves that are slightly different. This is actually a phenomenon that piano tuners use to tune the strings on a piano. They listen for beats. They don't want to hear any when they're tuning the strings on the same note, for example. For those of you who didn't know, a lot of the notes in a piano actually have 3 strings. Next time you get a chance, take a look inside of the piano. This might be, for example, 2 people walking together. Your legs are longer than your friend's, so you take fewer steps every minute, and your friend's legs are shorter, so she has to take more steps every minute. The difference between the number of steps you take per minute would be the number of times that you're actually stepping together, or basically beats. For sound, beats occur as kind of a louder, softer kind of pulsing. And here's why that happens. These 2 sound waves are slightly different wavelengths. You can see the wavelength here is slightly lower or smaller, which means the frequency is higher. At some times, these 2 peaks line up together and these 2 troughs line up together, giving you constructive interference. The sound is actually going to be louder during this point. A little while later, you notice that the trough of one matches up with the crest of the other. They cancel each other out. You remember that's called destructive interference. And same thing here, you've got the crest of this one matching up with the trough here, and it cancels out. So this is a region where you hear a slightly quieter sound. And then a while later, you've got constructive interference again. So this alternating between constructive and destructive interference creates this phenomenon where the sound gets louder, softer, louder, softer, louder, softer, louder, softer. And that pulsing is what's called beats.